On the left, the high-pressure tangle of an industrial water pipeline. On the right, glowing electrical pulses racing through the pathways of a printed circuit board. Many introductory physics courses teach electronics by comparing it to plumbing. In this model, water pressure acts as voltage, the rate of water flow represents electrical current, and a constricted pipe serves as a resistor. This raises a question about why two entirely different physical mediums, one made of heavy pressurized fluid, the other of subatomic charge carriers, obey such similar mathematical laws. Both systems are examples of transport driven by a difference in potential. Whether it is a difference in elevation driving water down a hill, or a difference in electrical charge pushing electrons through a wire, nature requires a gradient to generate motion. This shared mathematics reveals the underlying physical logic of how nature moves energy through space. Both systems rely on a single algebraic structure. The driving potential equals the physical resistance multiplied by the flow. Ohm's law, written as V equals I times R, defines how voltage difference across a circuit balances electrical current multiplied by resistance. In hydraulics, the algebra is identical. The pressure difference, delta P, equals volumetric flow rate, Q, multiplied by hydraulic resistance. Current is the rate of electric charge moving over time, while flow is the rate of fluid volume. Both pressure and voltage measure the same variable, the available energy per unit of the material being transported. As these materials move, the physical geometry of their conduit impedes them. Pushing flow through a long, narrow path increases resistance, while widening the cross-sectional area decreases it. The Hagen-Poiseuille equation shows how a pipe's radius dictates resistance. Because the radius is raised to the fourth power, doubling a pipe's width allows 16 times the volume of laminar fluid to flow under the same pressure. Whether the conduit is a microscopic copper wire or a massive PVC water main, physical dimensions manipulate the math of resistance using the same geometric rules. Fascinated! When we scale up from single paths to complex branching networks, the physical laws of conservation take over. Because electric charge and incompressible water cannot vanish, the total flow entering any junction must equal the total flow leaving it. And when these paths form closed loops, the potential added by a mechanical pump or a chemical battery must balance the potential drops lost to the pipes and resistors. We can extend this comparison to components that store energy for later release. In electronics, this is a capacitor. A capacitor accumulates electric charge the way a physical tank stores volume. As the tank fills, the weight of the fluid creates a back pressure that mirrors the rising voltage inside a charging capacitor. Similarly, an inductor resists changes in electrical current. In a pipeline, this is analogous to the inertia of the moving water itself. When a valve slams shut on a fast-moving flow, the water's kinetic momentum halts abruptly, creating a violent pressure surge known as water hammer. That mechanical shockwave mirrors the dangerous voltage spike that occurs when an inductor's electrical current is interrupted. Even in these changing states, the equations governing gravitational water energy and electromagnetic fields remain mathematically symmetrical. These two mathematical models collide in the physical world at a hydroelectric dam. Inside this structure, the gravitational and kinetic energy of the falling water is converted into electrical energy. The output follows the hydroelectric power equation, where power equals the system's efficiency multiplied by the water's density, gravity, flow rate, and the height of the drop. As the rushing water spins the turbines, that mechanical energy transfers up the shaft to the generators, producing the outgoing electrical current. A hydroelectric dam serves as a physical bridge, translating fluid dynamics directly into the language of electrodynamics. Despite this symmetry, electric current is not literally water flowing through a tube. Water requires empty space to flow into. A solid copper conductor is already packed with mobile charge carriers before a battery is even connected. Water transfers energy through mechanical collisions at the speed of sound. Electricity transfers energy via electromagnetic fields in the space surrounding the wires, moving at nearly the speed of light. Water can leak from a pipe and pool in an open environment, but an electrical current requires a closed loop to move at all. High-velocity water becomes chaotic and nonlinear due to turbulence, and there is no hydraulic equivalent for the quantum mechanics governing modern semiconductors. Ultimately, these equations describe the mechanics of flow. They represent a fundamental logic for transporting energy, revealing how nature organizes motion through a system, regardless of the medium.